All right, let's get into our last topic for Unit 3. And it's taking a look at what we did earlier in the week with coming up with our own ideas of what matter looks like when it changes, and really trying to understand that from the chemistry side, some of the terms and some of the different things I want you to know. So make sure you're taking notes on this because it's all going to be something that we want to know. All right, so we started with solid liquids and gases this week, and we ended with it last week, and just taking dinosaurs and turning gas. That's kind of like a fun concept. Kind of going back to our videos of macaroni salad also. And so you would have already watched my Ira Remsen reaction. So I want you, based on those observations you took, what about that told you as a chemical change? What about that told you it could have been a physical change? Okay, because we're gonna use that reaction as we go through today to talk about a few different things. All right, so make some note of that. All right, so we have this idea of physical properties of matter that are going to turn into changes, but we want to know what the properties are first. And what a physical property is, it's something that can be observed or measured without, and that's the key. It's without changing the identity, without changing what it is at its core. Okay, and what is it at its core is chemistry. It's the formula. It's a compound. It's the elements that make it up in that exact same pattern with that exact same system or number of bonds, right? And so we want to think in those terms, and we're looking at it with our eyeballs, but really what we want to be able to do later on this year is think about that in terms of what's going on underneath what we can see. And so we have an extensive physical property, which is something that depends on the amount that's there. All right. So what's an example of an extensive property? Okay. And same thing with intensive, right? Intensive is another type of physical property, but these ones, they don't depend on the amount you have, right? So what are some examples of physical properties that depend on what you or how much you have, and some that don't depend on how much you have, right? And we can observe them, and we can do that without changing what it is. All right, so think about that. Give me a couple examples. There's some of the things I was hoping that you would show me, right? And so an intensive property is something like boiling point, color, temperature, luster, hardness, right? It doesn't depend on what's there, right? The color of copper is always going to be the same unless we make a change to it. The boiling point of water is always going to be the same unless we decide to make a change to it and put something else in it, but that's changing it, right? And so those are always going to be the same, whether we have a crystal of salt or we have a big block of salt. Its hardness doesn't change, right? Where extensive properties do change, right? Obviously the volume, the mass, the size, the weight, and you can see obviously these are things that generally have a number of something that we can measure and change versus these guys up here that don't. All right, so those are some examples. Hopefully you talked about a few of them. So let's go on to chemical properties, right? Really why we're in chemistry. So chemical properties, these are the guys that that it can change, and because of their changing, because those properties are changing, they alter the identity. They change that molecule at its core, and so it becomes something else, and that's the key, right? Let me get me out of the way. And so what happens is we made something new. So when you change a chemical property or when you enact a chemical property, what happens is we made some new substance, right? This is what a reaction is. And so we have the ability to look for that and figure out if something new happens. That's easy to say when we're looking at a chemical formula. That's hard to say when we're looking at chemistry with our naked eye, right? And which is why chemistry is hard, is because of that fact right there. Move me up there this time. All right, and so there are some chemical properties, right? The fact that something's toxic, the fact that it has different oxidation state, heat of combustion, chemical stability, reactivity, bonds, enthalpy, flammability, right? These are different things that we're going to take a look at, mainly oxidation state reactivity, bonding, and flammability, but we're also going to talk about enthalpy a little bit that we talked about last year. And the stability, different things have a shelf life. When you have hydrogen peroxide on your shelf, if you wait too long at home, it might not be good. It might not clear your cut and clean your cut as well as you thought it should have or would have. Okay, so these are just a few variations of different types of chemical properties. All right, but definitely things you can't just look at it and know what it is, where physical, lots of times you can. All right, so what makes a chemical reaction? And again, these you should know. So we have reactants and we have products. The reactants are what goes in, right? They're the substances that are going to undergo the change, right? Then we have this yield sign right in the middle, right? So reactants yield products. Reactants make products. Reactants become products, right? After we've gone through those. So products are the new substances that are made. So just because we've seen a change does not mean that we've seen something new. And that's what we tried to prove earlier on in the week with those pictures I have. And we're going to try to prove that with some things that we actually see in front of our eyeballs, right? And so that's where the Ira Remsen reaction comes in. Whether you knew it or not, right? I gave you this. I gave you copper and nitric acid, but what we didn't know, we saw the effects, but what we didn't know is what was being created, right? So we have this copper nitrate, we have this gaseous, this brown gas, this nitrous oxide, the same thing that you would get in older dental chairs, right? And then we have water. But again, we didn't actually see any of that. We saw the effects of it, and that's what makes chemistry interesting, fun, but also difficult, is those. So we have our reactants that yielded our products, right, with our very first reaction of the year. So what were some of the evidence of this, right? And these are the things I was trying to get you to look at without me telling you in your note-taking ability. All right, so evolution of heat or light. And this would be much easier to do if we had done this in class, but I tried to tell you, oh, it's hot. And it was really hot, right? It was extremely hot. I didn't want to touch the bottom of the beaker. The top of the beaker was hot enough. And I didn't put anything besides acid and a penny in it. I didn't heat it up at all, right? And so when you get this release or consumption, when things feel cold, okay, that's also proof that a chemical reaction has happened. Okay, so we don't actually see the atoms turning, or the compounds turning into different compounds, but we can feel is heat or coldness being given off, right? So the production of gas, we saw that also. We saw all of a sudden this brown gas being produced. And it's not always a colored gas. Sometimes it's a clear gas, and sometimes those are the worst, right? Because we don't know that they're there. This one we did, and then I put it in the fume hood and let it suck out all those things we didn't want to breathe in because they are poisonous. And so we have the production gas. That's new. But the key here has got to be a new gas, right? It's got to be a new gas. It can't just be something that we boiled, right? We can't just turn water into water vapor. It's still water. We can still cool that down, and we have a liquid H2O. So it's got to be something that we produce as new. We have to break bonds and make new ones in order for this to happen. The one we didn't see is the formation of a precipitate. This is a pretty easy one to recognize because what happens is we generally mix things together like liquids, and all of a sudden we get this new solid to come out. We'll take a look at this one specifically when we do reactions, but I'll show you some different reactions. But we didn't see this one in this lab. There wasn't anything. In fact, the penny was gone. Like the one solid thing that we had wasn't there. Everything looked like it was a liquid. Like, maybe I could drink this and it's Kool-Aid, and you would still be in trouble. And the last one is a color change. And we saw lots of different color changes in this one. All right, we saw browns and we saw greens, and depending on the type of penny, I could give a blue. Now, to me, this is the worst of all of these, okay, evidences, because sometimes things just have a color, just like sometimes things just have an odor. And so there's lots of other evidences of chemical reactions that you could look up, but these are definitely the best four. When you see at least, two of these, you definitely know you have. But when you can mix color with the precipitate, or the formation of a gas with also heat or light being given off, right? They're definitely a chemical reaction. And always one of these shows a chemical reaction, but sometimes they can trick us, okay? And so we want to know that. And so we're going to get into our last main topic, and it's this idea of, and there's some parts to it, but there's this idea of law of conservation of mass, which is something that you should have been able to talk about before. But basically, kind of the father of chemistry that we'll talk about a lot this year is this man named Antoine Lavoisier. Okay, and he kind of came up with some of the first laws of chemistry. And what he said is matter cannot be created or destroyed. We'll take a look at this at different points during the year, which to me means, mass of the reactants must equal the mass of the products. And to put that in layman's terms, that means what goes in has to come out. But, okay, if we were to take this huge bonfire, right, which looks really cool. If you see these, this is huge because these are like, I don't know, 10-foot logs all stacked in front of each other. And there's a bunch of little people down here. That's a huge bonfire. My guess is the mass that went in would not equal the mass that goes out. Okay, why? All right. But really, when we talk about chemistry, this is exactly what should be happening. And the reason why that last one didn't work is because we didn't have this guy, right? What we had before was an open system. And here we have a closed system. Nothing can escape. And when nothing can escape, we get what goes in coming out. And we have a chemical reaction, and we have new things. And you can see we have barium chloride and copper sulfate, and we get barium sulfate and sodium chloride, right? This is a good example of a double replacement reaction that we'll talk about like in the spring, okay? So nothing you need to know now, but that's what's going on. Is if we can encapsulate, if we can collect everything, right, we would get the exact same parts and pieces. Okay, but when there's an opening, when we're open to the atmosphere, when it's not a closed system, which most of the time things are not, we don't see this. But what I want you to really know is in the end, yes, every reaction, what goes in comes out. It just depends on how well we collected it. All right, so I want you to think about that, and I want you to answer these questions. If I start out with a 24-gram sample of carbon, right, and it reacts with a 64-gram sample of oxygen, okay, and they form carbon dioxide. The first thing I want you to try to do is write your first chemical formula, and then I want to know the mass of the reactants, all right, and then I want to know the mass of the products. See if you can do it. And I'll give you the answer after in notes. All right, see what you can do. You can do it though. All right, so last concept that deals with that is we got to know about this other dude named Joseph Louis Proust. All right, and what he did is he also came up with a law, and he called it his invisible hand. And what he said is the world of chemistry, the world of nature is governed by this invisible hand. And what that comes down to is nature assigns these fixed ratios, these ratios that can never be broken. Okay, and so we're going to take a look at that as we go through right here. And so it's pretty simple. It's a pretty good idea. And it's this law of definite, oh gosh, don't do that. It's this law of definite proportions. And what definite proportions says is no matter what, when we have chemicals, no matter how many of them or how few of them we see, if it's that chemical, it's always going to be in the same proportion. All right, we'll deal with this now and a lot later. But elements of a compound are always presented in the same proportions by the same mass. All right, so if I have 4 hydrogen parts and I have 2 oxygen parts, anytime I make water, knowing it's H2O, right, that's going to be in a 2-to-1 ratio. Right? If I added a 5th hydrogen right here, I would still end up with the 2-to-1 ratio over here, but I would have hydrogen just wandering around by itself. Same thing with an oxygen. So what we get is the parts make up the whole, okay, in the exact same proportion. If this number changes, what he's saying is we have something new. Case in point right here. You found a clear, odorless liquid on planet Mars. Did you find it to contain, and you found it to contain hydrogen and oxygen, but did you find water? Right? When we look at these, one kills you, one tastes bad, and one is necessary for life. You could take your chances, right? But only one of these is water. So did you find water on Mars? I don't know. All right, one of these is water, one of them is salt water, and one of them is hydrogen peroxide. Which one's which? Can we tell by just looking at it? No. But once we get into chemistry and we start to do some of the math and we start to do some of the analysis, we would be able to figure it out and we would be able to make the correct choice. Here's another example with all the numbers there, all right, showing the law of definite proportions. And notice that no matter how many or how much we have, the same proportions are going to be there. Now we see them as masses, starting with the first one, but no matter what we've changed in the amount of mass we have, in the end, we're still ending up with the same proportion. Okay? No matter how much lead and sulfur I have, I can only combine them so many times in so many different ways. And once I do that, then I have leftovers, which is a huge concept we're going to talk about at the end of the year. But right now, we're just kind of looking at them as a whole. And so what I want you to do is I want you to kind of look at this data I present you and tell me which of these substances are the same and how do you know? Okay, think back to that picture I just showed you. What did you come up with? All right, have fun.